to go have a chat to him and say, look, this is why I've got into this field, to work on interesting and useful problems. How can I help? Started doing some research projects with them. It was mostly just in my own time to begin with, but we ended up actually publishing a paper looking at predicting mortality in ICU based on a research data set out of a lot of Australian and New Zealand hospitals. From there, I did a bit more work with them and basically continued honing my skills, did an AWS certification, just broadened my skills, did a bit more of, what does production look like, and then managed to land a job through, again, someone I met at the AI meetup locally. That was Nick, who is the CEO of Max Kelson, and said, look, I'm looking for work. If you're looking for anyone, let me know. And I ended up working there. So I think for me, the key thing out of that story is that obviously, you don't have to have a degree or a PhD in this field. You just have to have time. Hello, all our online viewers. Hopefully you didn't miss too much. Wasn't that important anyway. I think the key thing is you don't need a formal education. Don't get me wrong. It is great. If you've got, going through that path gives you a lot of skills and gives you, decent breadth. And a lot of companies will want those qualifications, rightly or wrongly. But, if you do want it and you're willing to, go and do the work on your own and I think the key thing there being on your own, you do have to be motivated and do it. You can make it very easily. And I think the key differentiator, if you are going down that path, is that if you can show projects under your belt and show that you didn't just do, a few Kaggle competitions, or you didn't just do what your uni professor told you to do, but, if you can show, hey, I really want this, I went out and did this because I was just really interested in it, here's something else I want to work on, that sort of energy and motivation is actually not that common out in jobs in the real world. So if you can show that, a lot of people actually sort of want you on board, particularly some of the smaller and more nimble companies. So, go out, showcase your work, get involved in community events, because if you want to set yourself apart, often the best thing to do is to reach out, meet people in person, spam them on LinkedIn, it may sort of not be your style, but it can be the difference between you landing a gig or not. So definitely encourage you guys to do that. You can even spam me. I'll even let you do that. So that's me. So let's get started on the summary of lesson 2, or maybe not a summary, but talking about some of the key concepts in there. Let's go for it. So if we look about what was talked about in this lesson, just an overview for anyone who may not have had time to actually watch the lesson. Jeremy talked about validation and test sets, a little bit on overfitting and training, and he answered an audience question on loss and metrics, which I'm actually going to talk about here. Obviously talked a fair bit about transfer learning and fine tuning, given that right now we're working with CNNs in the course. The state of deep learning. Talked about p-values and hypothesis testing and a lot of the issues with p-values. I'm not actually going to go in depth here, but there's a lot of literature on that. And I'll add some comments about at least the machine learning field there as well. And then we started moving towards production deployment, a little project working with the Bing Image API. And at the end, a little bit on the data block API. So I'm going to touch on some of these subjects. I'll share some additional thoughts, and then Sam has put together a great notebook which he's going to go through, so we can do some live coding. I believe Sam has shared a link to that notebook in the Discord channel for this week's lesson. So anyone following online or in here, you can download that one and run that and follow along. But let's move on. So first thing that I'll talk about is training and validation sets. So I think last week in the lesson and after the lesson when we were chatting in groups, and also there were a few questions online, a few people were asking, what is the difference between training, validation, and test sets? When do you use what? So I thought I'd just touch on that. The whole concept of training and validation sets is really about trying to simulate what's going to happen if you train your model on your data set and then you go to production and you're running it on data that the model's never seen before. That's the whole idea. The idea is so that whatever results you do see are actually going to be reliable. And so the way that we typically do that, best practice is to use a training, a validation set, and then a test set. So for each of those, your training set is the one that you're obviously training a model on. So every time you train a model, every type of model, you should be getting some metrics on the training set. Sometimes people can actually ignore their metrics on the training set, which is actually a really bad idea. You want to be tracking and checking your metrics on your training set, because this is the only way for you to know if you're overfitting or if something's going wrong in training. Second is your validation set. So each time you've trained a model on your training set, you're then going to test it on that validation set. Your validation set is typically, 10 to 15% of your data, something like that. And essentially, this is going to tell you how well did each set of input parameters, maybe some different transformations on your data, all the different knobs and levers that you can move when you're selecting and tuning your models. This is going to be your sort of ground truth that you test it against. So, every model that you train and test, you should have a set of validation set metrics. And until you land at your final model and you've tested everything you want to test, you've run out of time and it's got to be deployed, you haven't touched your test set yet. The only time you touch your test set is to produce final model accuracy metrics, and those are the ones that you report on how well the model works, right? So you should only ever touch that once. No hacking and checking that and coming back and tuning against that. That's naughty. There is one other thing that you can do as well, using cross-validation. It's a really common technique. It's a useful technique as well when you don't have as much data. Essentially, the idea here is that you'd still have your set-aside test set, but instead of having a set training set of, say, 70% of the data and then a set validation set where you have the same examples in each, what you'd actually then do is you'd train a model sort of 5 times on different slices of that sort of 80% of data. So you might train it on 60% of it, test on 20, then you'll move to a different cut of that data, test it on another slice, and you might do that 4 or 5 times. And the useful thing about using cross-validation is that if you can imagine that when you cut your training, validation, and test set up, you're slicing it up in one way. And so what you might find is that there might be specific examples that only end up in your validation set or your test set. The downside there is that, your model might happen to perform really well on that validation set, but if you were to take a different slice of data, there might be other examples in there that the model performs, particularly bad at, particularly if it's overfitting, for example. So one of the benefits of cross-validation is that you get that sort of validation metric over different slices of the data, and then you can actually look at the variance of those metrics and make sure that it's not too wide. If you find that you do cross-validation and you get 5 different numbers that all vary quite a lot, then there's probably a problem there, and maybe your model's overfitting or needs to be regularized, or maybe your data set isn't shuffled quite the way it should be. So something to keep in mind. If there's any questions along the way, feel free to ask them as well. One other thing on training validation sets, as I said, this is to simulate what we do when we go to production, and within that, there's a key assumption that we have when we are doing these splits, and that's that, let's say we've got our data set of 1,000 examples that we're going to do our model training and testing on. We slice that one up. There's a key assumption that this data that we're using to train and test our model is the same as what we're going to see in production. And there's a term for that, independently and identically distributed, IID. If your production data is from a different distribution, maybe you're training a model on data from Australian hospitals and you go and try and use it in the US, that distribution is going to be different. So, when you're training and testing your model, those metrics are only valid assuming that your model is going to be used on that same data. Something really important to remember, and something that can sort of sneak up on you as you start to use your model in different applications. One other thing along this way, when we are doing this splitting, we don't always just randomly split our data. We need to be really, really conscious that we're not letting our model cheat due to data leaking in between your training and validation set. The idea is that, anything in your test set your model has never seen before. So sometimes, in your data set, you might have multiple observations of the same medical patient at different points in time, or different CT scans from that same patient. You want to make sure that you're not now just splitting on the image that you've got, or the test that they came and did. You're actually splitting on the patient, because there's going to be unique characteristics to that patient. Maybe their age, gender and ethnicity is unique, and there's no one else in the data like that. Your model could just learn that and then just learn it for that patient. Your metrics aren't going to work anymore. So you need to really think about that before you select a method to split your data. In that example with patients, you might split on patient ID, save your patient IDs into a different set, and then assign the images or the examples from that patient to the actual set that you train your model on. With time series, you might use something like a time series split to sort of walk forward in time rather than just picking random slices to train and test on. And there's actually a cool little visualization. sklearn has a bunch of different data set splitting functions in there. They've actually got, as part of the documentation, a nice visualization of, I think it's about 10 different approaches for how you would do data set splitting. And it's a nice visual way of getting an understanding of the types of things that can go wrong and the types of techniques you might use. Cool. So last week there were a few questions on training loss and accuracy or performance or evaluation metrics. Thought it was worth touching on here and diving into a little bit of the intuition. This will actually be covered a bit more in depth in future weeks, but given that there were questions, I thought it was worth touching on. So just to go over, the difference between the two. So a loss function, like an evaluation metric, is used to assess how well our model performs. But there's one key difference between them, and that's that a loss function is a smooth function. So as your model gets better or worse on a single example or a group of examples, minute changes in your model's performance on that example lead to a direct change in the loss metric for that example. Whereas an evaluation metric, often what you get are these sort of steps in your accuracy as your model gets better. Now, when it comes to doing backpropagation for a model and training that model, it's really important that you have a smooth function so that as you backpropagate your derivatives back, your model's training smoothly. We will dive into this a bit further in later weeks, but I thought a visual example actually helps to sort of explain this. If you imagine that we've made predictions on 5 examples here, each row is an example. Let's say that this is as a model trains, right? So this is the same example, and the true class is 1, and after our first epoch, our model is actually predicting 0.3. Now, because that's less than 0.5, our accuracy metric there is 0. We haven't got it right, we get 0. Our log loss, on the other hand, which is one of the most common loss function for when we're doing classification with categorical target variable. That one there is 1.204. And if you look over here, you can actually see, if our true label is 1, what will our log loss be based on our model output? It's important to remember here that when we have a classification model, as much as the model's predicting a class of either 0 or 1, under the hood, we actually get a continuous number between 0 and 1. And that then gets converted to either 0 or 1 based on whether it's above or below 0.5, which is the typical default threshold. So the key thing here is that if you were to use accuracy as you train this model, and let's say our model gets more and more accurate, the first epoch it predicts 0.3, then it predicts 0.45, then 0.6, it's getting closer and closer to 1. What you'll see is this accuracy score goes from 0, and there's sort of not really any information whether the model's learned anything new from the first to the second epoch. But then once it ticks past 0.5 up to 0.6, suddenly now your accuracy jumps to 1. And your accuracy stays at 1 as your predicted sort of class probability moves closer to 1. And that's not really that handy when we're training our models. It doesn't let them train as efficiently as they could. On the other hand, when we use an actual loss function like log loss or binary cross entropy loss, same thing, that actually decreases really smoothly. And as we get closer to the true value, it decreases, in decreasing amounts, so to speak. So I thought it was worth touching on. It's a little bit in the weeds, particularly if you don't actually know how these models work. But a really important one to remember is this graph here, where the further away you are, the steeper this gets. Whereas with accuracy, it's actually really steppy. Does anyone have any questions on that? Cool, perfect. All right, next slide. So, when we are training models, we are trying to track these metrics, and there's a few things to keep in mind. And we are going to look at some sort of loss curves, and we're actually going to work together to diagnose these and see what's wrong. But first, there's a few sort of rules of thumb that you want to keep in mind when you are looking at these graphs, when you've trained a model and you spit out your sort of training loss and your validation loss of how to know what's actually happening within the model. So there's a few here. I wouldn't say these are all of them, but the first one is that you really want your training loss and your validation loss to be close together. What this means is that, when they're close together, it means that, the data in your training set and the data in your validation set, have a fairly similar distribution. There's a similar amount of variance within them. And it also means that, your model is capturing enough sort of information, learning a good representation of the data, that it performs pretty closely on both. You don't want to have a big gap between them. It means that your model's probably not powerful enough to capture all the variance and just learning what's in the training set. It can't generalize. The second one is that your training loss and validation loss should decrease pretty smoothly. If it's not smooth, your data set or your batches could be too small, or maybe you haven't shuffled it correctly. And as your model's moving through different batches of all your data set, some of them it's doing really well on, and others it's doing really badly on because it hasn't seen them yet. So that could mean that it's not shuffled randomly, so that the model's sort of seeing the whole distribution of the data as it moves through. The last one is that your training and validation loss should gradually flatten out. If they haven't flattened, then and even if they have sometimes, your model hasn't actually finished training. And often what can happen is that people actually train their models. Their sort of training and validation loss will sort of flatten out, and then because it looks flat, they actually just stop training their model and they think that it's ready. And there's a number of papers out there over the years where you look at the sort of training metrics and there's a really steep sort of drop, and then it takes forever for the model to slowly get better and better. And a lot of people just stop training their models before their validation loss actually starts increasing. So I've put in here a link here to one of Andre Karpathy's blog posts about tips for training neural networks. It's a really, really good blog post. I think it's the second or third step, is that the first thing you should do when you're choosing a model is actually try and overfit. The reason you want to overfit first is to make sure that the model that you've chosen is actually powerful enough to actually learn the data set. If you can overfit, then okay, my model can capture the variance in the data set, it can learn, and then what you want to do is then start to apply regularization so it can generalize to the validation set. Don't worry too much about really understanding all that just yet, but that blog post, save that one and check that out because it's a really, really good one. So let's look at some loss curves and see if we can figure out whether they are right or wrong. So obviously our training is... Sorry, I thought I heard someone saying something.
Are we going to get these slides?
Yes, I will share them with all of you. It will be in the channel. I think Sam's notebook is already in there. So for this one, our training loss is down there really low, and then we've got our validation loss, which is, 8-9 times higher. So does anyone have any idea what the diagnosis would be for what's going wrong with this model? No?
Well, the validation set's not representative of the training set.
Maybe. So it looks like the model's learning something from the training set, right? But then when you run it on the validation set, it's not generalizing. So it's not working very well on the validation set. So what that means is that your model's actually underfit. So remember how we talked about, essentially the model is not powerful enough to capture enough variance and then generalize to your validation set. So your validation metrics are terrible despite it working really well on your training set. And this is all from a blog post, by the way, if you want to check this out. There's more detail in there. Next one. What's happened here? So training and validation loss are nice and close together, but they're still really steep. So where's this model and what could we do to improve it? Not enough training, still learning, perfect. So yeah, model requires further training. It's really good that both of those are close together, but yeah, it's still going down, so we just need to train that further. Next one. This one's a bit squiggly. Any ideas?
Quality mixed data set.
What's that?
the poly-mix data set from the other side.
That's it.
The other slide.
Yeah, so there's a couple things here. So what we find is that our loss is going up and down. So the data set so the training set might be a bit too small. So as it's learning, it's sort of pushing one way and then pushing another. So then when you go to your validation set, it's going up and down. And yeah, also too small. Next one. So this one looks quite good. It's fairly stable. There's always going to be a little bit of up and down, but what do we see here? Perfect. So as you can see, they've both come down together nice and close, which is a good sign. And then as as they start to sort of converge, they both start to bottom out, but train keeps getting a little bit better. It's now really learning the intricacies of the data and starting to overfit. And validation is, coincidentally going up. So once they start splitting apart, and you'll notice too that your validation is not just diverging from your training, but it's actually getting worse on the graph. So it's going from sort of 0.42, ends up at sort of 0.44. It is actually getting worse. Final one, I think. What about this one? Is there anything wrong with it? Looks all right. Perfect. So this is a good fit. This is what we want, right? Training and validation, really nice and close together. And then they've both sort of bottomed out for, many epochs. They're not really moving anywhere. This is what we're looking for. This is ideal. It's not often that you find your training and validation right on top of each other like that. But if you do, that's great. Final one. This is actually an example. So sometimes, depending on how you train your model, you might actually see something like this where you sort of have your metrics or your loss, drop down and sort of slow down in how long it takes. And then suddenly you get another drop again, and then it evens out and it goes again. This isn't anything that's necessarily wrong with the model. Typically, the reason you'd see this is actually because as you are training for more epochs of your model, something like altering your learning rate might happen, or changing augmentations in your model. Basically, dynamically changing the way you train your model can lead to something like this. And this is often something that you see with learning rate annealing in different techniques. It often isn't as pronounced as this, but you will sort of see sometimes curves like this. So if you see something like this, it's often about your learning rate. Cool. And there's that's just from a paper. I wouldn't bother reading the paper, but it was just a good example of the graph that I could find. Cool. Any questions on loss functions? We will go over this a bit more on the course.
If your model has just the right complexity for the variability in the data, would it be the case that you could train it for an unlimited number of epochs and not have the training and validation diverge?
Theoretically. Assuming you have enough regularization in the model, but typically it will start to overfit and you will see it diverge. So it'd just be about whether you've got your regularization correct, because it'll start to try and jump down local minima, but if you've got regularization, you won't let that happen. So it's really about how you train your model. Typically you're better off having it with the capability to overfit and then stopping it before it does, essentially. If you get it right, it's not going to suddenly become an overfit model and be terrible. So yeah, there's still a bit of magic in this, obviously. You can sort of automate a lot of this. A really good example is just early stopping. You can just let your model train, and your metrics will go down. And once you're, every sort of epoch, you just check, right, what was my validation loss on this epoch? Is that my best loss? And if you find that it starts getting worse, you basically just let it keep training just to make sure that it wasn't just one batch and then it starts to get good again. Basically, once it, keeps going for maybe another, 5 or 10 epochs or whatever, then you go, okay, the model's definitely overfitting, throw that away and go back to that model. And you save those weights there. You don't let it overfit and then keep the weights over here. You sort of track your loss if it's your best loss, save the weights. Next epoch, if it's better, throw those weights away, save these, and then as it gets better, stop and come back and take those. That's how you do it. Cool. All right, transfer learning. So obviously a huge amount of this course is going to be using transfer learning techniques. Rather than, obviously models require a lot of data to learn things, particularly neural nets, because there's so many parameters in them. But in order to make that easier, we use transfer learning, and this has really made it. This is the reason why you can train models in like a couple minutes, because most of the hard work has already been done, and it is standard practice across many domains. Maybe not most, but particularly in computer vision and NLP, you just don't really do anything else unless you're Google or something like that, training something from scratch. So essentially what we're doing is we're using another larger data set and a model that has learned from that data set to learn the representation of the data and sort of the useful ways of extracting features from that data. And then we want to actually reuse that representation. There's actually a sort of a subfield of machine learning called representation learning. And the whole idea of representation learning is that, you know, you might pass your input data, which makes sense, maybe a picture, it looks like a picture to us, you know, our receptors make sense of it. Once it goes through the model, what you find is that in the middle, to varying degrees, it actually doesn't make much sense to humans, and sort of the model, in order to make sense of it, puts it into this high-dimensional mathematical space in order to sort of relate different examples of data to each other. It's not interpretable to us, but that sort of like concept is called like a representation. And so essentially what we're tapping into is that when we're doing transfer learning. We sort of learn that good representation on one really big data set, and then we sort of reuse it in our problem. So, you know, the obvious thing here is to, when you are doing transfer learning, you wouldn't want to transfer learn off a black and white data set where the model's only ever seen black and white, and then try and use that on color. It could work, but you'd have to train it a fair bit more. It's not as efficient. Likewise, you know, at a more finer detail, the types of sort of context or style that the model has been trained on does make a fair bit of a difference. So one thing that you generally want to do is, you know, if your problem is looking at satellite footage, aerial imagery, try and find a model that's already been pre-trained on that same type of data. Likewise, if it's CT scans that might be black and white, try and find another data set or another model that's already been pre-trained on that. It's not a deal breaker if you can't, but it will just mean that you can train a bit quicker and maybe get a little bit more performance out of it. I've put a few links in here that actually sort of dive into different representations in data. You might find them interesting. They do get a little bit more advanced, but it does help to understand, you know, what's actually happening within these models. And Jeremy touches on some of the same stuff in that lesson. Here's an example of sort of text. When you actually do language models, you find that all these words end up in this high dimensional sort of space, and what you find is that words that have a similar semantic meaning end up sort of in a similar space together. So this is an example of that, but there's heaps of those around on the internet. Anyway, moving on. Next thing to talk about is model architectures. So I think there was a question last week about, you know, how do you know when to use which type of architecture? And a model architecture is really, as a human, us trying to help the model learn important things in the data. And so what we do is we sort of construct the pipelines for the data to run through and the ways that this model is going to process the data based on what we already know about the data. So for example, if you look at, you know, images, one of the breakthroughs back in the 2012 was, you know, convolutional neural networks. And the key breakthrough, the reason why that was a breakthrough, was that these convolutional filters are actually really good at extracting meaning from pixels that are right next to each other. If you were to use just a fully connected neural net, what you do is sort of take the top line of pixels and put them here, then you take the second line and put them here, and then the third line and put them here, and it's not really clear to the model which ones are next to each other and which sort of pixel leads into the next. And so they just didn't perform that well because there wasn't really clear how it all related. CNNs, on the other hand, sort of progressively sort of start really zoomed into an image, zoom out, and you're doing a lot of the work for it by sort of telling it how to process that image. Yeah, so if you're looking at, you know, different architectures, there's often going to be small little improvements on the CNNs. There's heaps of different types. In general, the best thing to do is basically just go like papers with code if you want to have a look at what's the current cutting edge approach. And you know, some different types of problems will have different architectures and approaches that are going to work better. But having said that, let's say you've got even a ResNet now, which has been around for a number of years, compared to an efficient net, or maybe even some of the transformer models for vision that are becoming quite popular. Typically what you find is that a newer architecture from last year to this year, you might only get 1 or 2% additional accuracy on a data set. Often what you find by using a newer model versus an older model is that often you can actually get larger speed improvements. So your absolute accuracy typically won't improve that much year to year, but the amount of performance that we can squeeze out of smaller models will typically jump up in a much faster amount. So you might get sort of a 20 to 50% jump up, maybe not that much year to year. It just depends on the type of problem. So I guess the key thing is don't worry too much about trying to use the absolute latest model architecture. Use the one that's already integrated into your library, whether it's fast AI or something else. That will get you most of the way there. You can worry about squeezing extra performance out later on. Cool. There's another sort of slide in there that Jeremy talks about managing risk. I think there's a couple of questions on the questionnaire as well about how do we manage risk of models going to production and making erroneous predictions, or just stuff that could be mission critical, and we just want to have checks and balances in place. So this sort of diverges a little bit from the course, but I know a few of you are quite interested in this. So machine learning failures in production, unlike software engineering, are actually often a lot harder to detect. It's not a matter of something throwing an error because the data just didn't fit through the model, or something broke. Usually it's silent, or it's nuanced. You don't necessarily pick up on it, and it can be something that happens slowly over time. And so that's quite challenging, because it's not just a matter of checking the alerts, unless you've set up good alerting. It's something that you really have to think about along the way. And particularly because these models are sensitive to the data that comes through them, and data will naturally change over time. It's usually guaranteed, so it's something that will typically happen for most models. So the ways that you can actually manage this risk, and this sort of leads into some of those questions, is that first thing is you just always want to have regular model retraining. You want to make sure that you've got a big data set, a representative data set, and if you deploy a model today in June, as time goes on, the data that's coming into that model is going to change as well. A great example of this is COVID. A lot of the patients going into hospitals for chest scans, had pneumonia. COVID happened, and there would have been somewhere different models looking at these chest scans and making classifications on them. Suddenly you've got all these patients getting scans for COVID, and it's a bit different to pneumonia, and these models are starting to make predictions that aren't actually calibrated for COVID. It's never seen it before. And so this is why it's really important to make sure that you are training that model regularly. You can do a bit of analysis to understand how often that needs to happen. And then you also actually want to monitor the input data and the predictions of the model. So often what you can do is you can go, right, show me the last 1,000 predictions. What's the distribution of those predictions? And if that starts to shift a lot, it's usually a good indication that your input data is shifted as well. Likewise, you can actually also do the same thing to your data. It doesn't work quite so well on images and sort of data like that, but if you had, age, gender, like tabular data coming in, it's a lot easier to monitor that and then put some alerts in place when that starts to shift a bit too much. Next, if you do have a model making predictions in mission critical scenarios, have a human in the loop. Have someone reviewing those. Consider it decision support, which is the common term in medical applications, especially if you're trying to dodge FDA regulations as using AI as a medical device. Have your model make a prediction and let a human review it. A useful thing here is not only give a prediction, but also use model explainability techniques to show, right, here's the prediction and here's why the model made the prediction. Maybe it was this piece of the image that it looked most at or activated the gradients the most, or these input variables that cause the biggest difference in that prediction compared to just your average person in the data set. Next is also, when these models make predictions, particularly classification models, these models are going to give you a score between 0 and 1 based on the output of that final softmax layer. But that actually, it's fairly correlated with how confident the model is or how sure it is. But what you can find is that if you've trained on a bunch of data that comes from a distribution like this, and then you feed in one from over here, because you've got a whole bunch of non-linear sort of relationships within this data, if you feed in a new piece of data that's outside the distribution, you don't really know what the model's going to come up with. And sometimes the model can come up with a prediction that's 0.99, I think it's this class, but the model's actually never seen it before. It doesn't know. And so there's additional techniques that you can do that, along with getting a prediction out of your model, you can also then get a measure of uncertainty. This is something that's becoming a lot more popular in the field. There's a lot of new research coming out. It's a lot more accessible to actually build models with these techniques. And it's a useful way to sort of pair a prediction with a measure of, okay, but how much should I trust this? Something to look into maybe after the course. And then another thing you can do from a practical standpoint is if you've got a model making predictions, you can actually sort of, threshold the outputs of that model. So if you've got 100 insurance claims coming in a month and you want to automate those, but you know that there's always going to be sort of 20% of them that are really hairy or there's not enough information in the claim description and things like that, what you can do is train your model on a data set and then sort of, use a threshold so that if the model makes a prediction that's either less than 0.1 or above 0.9, you take the model's word for it. But if you get something in the middle that's closer to that threshold between where it could be one class or another, you send that one to a human and you have the human figure it out. The benefit of this is that most of your errors in a data set are going to happen in that sort of middle range where the model's not that sure if you've trained your model correctly. And so what you can do is sort of, instead of getting 80% accuracy on the entire data set, well, from experience, there's actually a model that we've got deployed right now that over the entire data set, the accuracy of that model is 83.4%, I think, if you analyze it across every example in the data set. But if you threshold out, I think it's about 15%, the 15 most ambiguous ones, the model actually goes to 97% accuracy. So you can automate over 80% of that data set and almost perfectly, and then just send the rest to humans. You've got an 80% efficiency gain, but your accuracy is so much higher. So that's a cool technique that you can use in production. It's really easy to implement as well. Cool. Final piece before we jump over to Sam is on data loaders. So data loaders are really one of the really key building blocks of how you train deep learning models. Getting, when we're using a GPU on a computer, there's a lot of computation happening. And it's really, really important that we get that data onto the GPU efficiently. Also, if we have to apply transformations on that data, often it's quicker to do that on the GPU. And so data loaders are something that you find in most or all sort of neural network libraries and really help us, funnel that data and split it and do all that correctly. So, the fast AI data block class, allows us to sort of get those data loaders and a really easy API to get that out. In the sort of order that it works, first thing is just loading the data off the disk or maybe from some feed if it's a little bit more advanced, sort of streaming the data in. It'll then take all that data and sort of split it into the input data and the target variable that it's looking for with those getters. It'll then organize the input data into the required blocks so that when it funnels it through the network, it knows what's an image, what's the target variable, where does the loss need to get applied, things like that. Any transformations that might happen, such as resizing or augmentations and things like that. And then finally, it'll do that splitting as well. So Sam's going to sort of come up and walk us, well, we're all going to go through this notebook. So there's a bit in there about data blocks as well. But this is something that you want to get comfortable with. You want to do a bit of exploration on this because this is something that you'll be working with quite a lot. Fast AI has a number of examples of different problems that you can solve, and you can basically copy code if you want. But if you can, learn how to use these data loaders, particularly understanding these blocks of image blocks, category blocks, and different things, and you can actually start to sort of modify and do new types of problems really well. Maybe you want to do classification and regression, stuff like that. Cool. Sam, take it away.
All right. Howdy, guys. Thank you very much, Michael. That was really informative and a lot of, I think, really helpful productionizing tips there and ways to mitigate risk. I've got some some code here that hopefully you've had the opportunity to look at. I posted in the Discord to get it out there, so that yeah, you had the chance to look at this before I go over it. It's 6:48 at the moment, Michael. How long should I go for? All right, we'll shoot for 20 minutes for this. Okay, so with Jeremy's presentation, he references p-values and null hypotheses, and I initially wanted to dive into that a little, but really to do that justice, you kind of have to be like looking at the data first and perhaps doing some cleaning and that kind of thing. So I thought we better kind of try to do things in the right order here a bit. So let's just start by having a bit of a look at some data. With these early cells here, this first cell here, I'm installing some libraries we'll be using later. So Pandas profiling is a very powerful tool for getting a report out for what a Pandas data frame is looking at, which we'll be seeing that report very soon. And the Kaggle tool there for perhaps downloading some data off Kaggle, and Seaborn is a plotting library. And you've already, of course, imported the Fastbook. So we import some libraries. I've got some code there that you'd have seen already from the Lesson 2 notebook for organizing your local Bears data set through the Bing search API and that kind of thing. But just to do a bit of exploration, if you were wanting to, potentially compare like means and distributions and form theories about the data and that kind of thing to perhaps do a null hypothesis test, let's have a look at some Kaggle data. So I just downloaded this data set off Kaggle. The exact data set itself isn't that important, but Kaggle's certainly great for playing with data. So this is just a heart data set with not that many columns here. You can see the rows is 303. And by looking at the data frame info there, we can see we don't have any nulls to worry about. And what it currently thinks are the data types, but that's because we're representing categories as numbers here. So what we find when wanting to train a model, you can't really escape from some specification of what the data is. There's not enough information in and of itself to fully interpret this data frame without us supplying this fact that some of these things are categories and that kind of thing. All right, so my report is finished. Let's see how we go. So this is that Pandas profiler tool, and of course in the old days you might write a hell of a lot of code for trying to look at a data frame and all it might contain, but in modern times to do a bit of exploration you'd use a library like this that'd give you.
Where can we find this one?
It's in the lesson 2 thread on the Discord. This notebook is posted.
We posted at 5 p.m. So if you're looking at the times, for 5 p.m.
So we can get overview information here. We can get some warnings here. It's letting us know there's a duplicate row. It's letting us know we've got highly correlated columns. That would be possible. If you've got highly correlated data, it might be you've got redundant data. So there's the possibility if correlation is high enough that you might drop data that's unnecessary. You may want to examine just like a single column itself, like age, like this, to get a distribution, to see how many distinct values are if there's a category. To determine what's missing, determine what zeros, to try to track down if there's outlier information. After a while of looking at like single column data, you might look at multivariate data or interactions between the columns. And so here's an example of a plot of this column here versus age, and I can't see that much of a relationship, but obviously with the right displays you can track some relationships. So I'll show you some more, but just to get through this report here, you can see the report also contains correlations, for example, and more than one kind, because there's more than one way to calculate how much we perceive these variables are changing simultaneously with each other. But if a feature has very little correlation with the output, chances are you might drop that feature, right, if it just seems unrelated to the output, or you might drop rows with missing values. I'm not trying to do a definitive data exploration process here, but just trying to introduce it, obviously. So in future lessons, I think we will explore a little bit more on data fallacies and tabular data exploration. So we'll be diving more into these concepts in the future weeks. But yeah, so that's that report and some samples. All right, so yeah, that might be a whole lot of code that you don't have to type if you just use that function, that reporting function. So here's a cell for dropping duplicates. Here is a cell for creating our own custom histogram plot, plotting two-column, well, no, a histogram, and then column distribution of it if you wanted to highlight stuff. But perhaps more interesting might be, say, plotting different categories versus the output. And when you're trying to explain model results and how confident we should be, if you've got small minority groups in the data set that aren't very well represented in your data, then if you've got these small, low represented minority groups in your data, then yeah, your model may be quite poorly trained against them. So as part of your data exploration, you'd be trying to see what are the different subcategories of data that we have, and are they well represented in my data set? If you've got massively more of one gender or ethnicity or that kind of thing, obviously your model performance will vary for those. And just on average, if you can create a plot that is visual rather than just looking at numbers, I think you'll communicate much faster with yourself and other people. Like, you can spot basically the higher numbers in this chart quite quickly, in a sense, although this is not a well done correlation heat map, because you might want it to go from, say, +1 to -1, so keep in mind your axes. But in the report, it has another one. But just that using colors communicates faster than trying to track numbers with your eye. All right, so we're working with fast AI, which is sitting on top of PyTorch and working with data. And how do we work with this data? People sort of ask, like, show us the kind of A to Z of a process. And that's a little bit tricky, because you have to kind of, there's a fair bit you may want to explain. But just touching this process on how do you kind of create a data transform process, you might initially think, I have to build my own custom class, which could be quite the mistake if you're ultimately kind of recreating a whole bunch of code that has already been made. So really, you're trying to track down someone else's class that is the perfect tool for the job. So if we've got a bunch of data, we might create calculate the mean function, but really probably we should be using the stuff from other libraries. Fast AI offers us many upgrades for existing sort of general use case classes that are out there. There's a standard PyTorch tensor that instead Fast AI gives us an upgraded tensor. There's lists and arrays that you might use, and Jeremy offers us an upgraded list, trying to give us extra functionality, basically, to make life easier. So wherever you can, you use the kind of upgraded tool that dodges away from common mistakes. So, you know, if you were diving into creating a custom PyTorch function, you might be looking at code, well, not really quite like this, obviously, but something like this top line, perhaps. If you're managing a change of transforms, something that you have to manage in addition to if you were looking at just the kind of math equation where it's sort of saying, oh, you're going to take a sum and you're going to take a log and that kind of thing. You've got to manage also the data type and the dimensionality of what you're working with, because some of these...
Could you zoom in a bit? It's small on the screen.
There we go. Awesome. Thank you for that. Yeah. So other than the math you might see for an equation, like in addition, the sort of unspoken part in that equation might be managing dimensionality, in this case, for this particular example of implementing from scratch log softmax. You have to have this unsqueeze term in there to adjust the shape of the output tensor. And so we can see the progression of that shape there for that equation. Of course, normally you wouldn't bother to reinvent the wheel on something like this. You would use, PyTorch's existing function for you to give you the same result. But these functions, in the end, are just kind of a name for a bunch of things in a row like this, right? And so they're useful, helpful abstractions that mean we don't have to reinvent the wheel. The fast AI version for some of these transforms, they've got obviously a transform class as well. And part of what you want out of a transform is often this ability to go backwards and forwards. So if you've got only this one-way transform and you don't know how to now look at your data and re-represent your data for yourself, you may get in trouble there. So as part of the functionality that you would tend to want for a transform is this setup where you've got this initialization process and encoding process to prepare potentially for the transform, and then a way to undo it. And so when combining a bunch of these organized transforms, and like a use helpful abstraction for tying those together is a pipeline. And we can see an example of that here. We're now calling this single pipeline calls multiple transforms. And so where this kind of leads us is towards the data block. And why is the data block so helpful and such a useful representation to kind of really be a powerful all-purpose data loader type thing to get our data where in the state it needs to be for the model. And so it has to have this capacity to specify all that we would want. And so in a way you can look at the data block as guardrails. If you could remember all of these transforms, you could kind of code this all up yourself type thing in a way. But the data block is giving us this guardrails to this is what you're going to need in order to get a proper functioning data loader. You've got to specify how to interpret, for example, the inputs that you might give it. You might have multiple categories of output or multimodal data where you've got the first bunch of bytes as an image, but there's another bunch of bytes that's something else. So you have to explain this stuff in enough detail for the model to be able to interpret it without making ridiculous assumptions. And so that's what this is. Guardrails basically to give you the minimum amount of code that you need to basically describe your data for the task ahead. So all of these functions that you see here can be inspected in this manner that I'm doing here. So you can just go piece by piece to have a look under the hood at what anything here is doing. And it's a really good way to see quality code often enough as well. So you might think you could easily rewrite the way to randomly split data, but in fact there's many kind of classical ways to make a mistake that really we want to really dodge, because if we accidentally not correctly create the random splitter that we need, it can poison, a whole day of training or a whole lot more, right? So much of this is trying to be really certain that we've done something correctly. And so, if we really don't need to reinvent the wheel, we shouldn't. And so here we can see a powerful example of how you might approach creating a random split in your data set with this information. In the end, you could create your custom version for a data set, but of course, fast AI offers us many different options here for upgrading our data interpretation. So there's different kinds of splitters that we need for different kinds of data. This get Y term here is for interpreting the Y data. So this parent label function that I was showing before. So label item with the parent folder name. Of course, in your project soon, your group project, and I believe we'll be diving into the group project information after this notebook, you'll have your data set where it'll need to be interpreted in some way before it goes into the model. So there's all likelihood that maybe you'll be writing a function like this that's going here, right? How do I interpret my label so that it's represented well for the model? Or how do I interpret my input X value so that the model understands it? So that's the kind of likely stuff that you will be needing to customize for your projects ahead. You should have seen the process for training the bear learner and how to play with that, hopefully. All right, well, any questions on what I've been talking about so far with this stuff? All going good? Excellent. Awesome. Fantastic, guys. So something that, like, for the task ahead, what you want to get good at is you will be needing to do some transforms from time to time. So I've introduced some of these concepts, but for example, working with an image project, how powerful your augmentation is a magnifier for your data set scale, in a manner of speaking. So it's a way to multiply the amount of information, the apparent information the model gets access to, in a sense, because you're helping it understand what's noise by changing something about the image that's only noise. So all the augmentation is a way for making up for the inadequacy of the finite data set that we show to the model that doesn't fully represent what is noise or not. Incidentally, a theory about dreams is that serves the same purpose for helping us not overfit to our memories, but that's just pop psychology. Okay, so in terms of augmentation transforms for images, certainly Jeremy's put a lot of thought into this because obviously fast AI is crushing it on image classification in many ways. But here we can see some of the augmentation that you may be applying to an image, but not all of these should be applied depending on your circumstance. If you had, for example, a downward view on the data from a satellite image, you could do different transforms perhaps than if you had a view that was looking out from a car. You wouldn't fully rotate an image to be upside down from a car, or maybe you would, depending if what you thought the circumstances that car might get into. But you would typically subselect some of these augmentation transforms. And as Michael said, you start by overfitting and then you try to kind of beat it back with more and more aggressive regularization strategies. So if you went too crazy on the transforms initially, the model might struggle to learn. So with these things, you can kind of get more aggressive with your regularization as you go forward, rather than starting too hardcore. All right, so we can see some of those transforms there for that data set. And there was a question in the thread about what if we wanted to train further. So we will be diving more into the training process in the weeks ahead. There's a few tricks here and there for the process of training on a large image data set and progressing that training process that we'll get into further. But just to kind of initially answer that question in a basic sense, in that you can't quite just call fine-tune again if you wanted to train further on data like this, because it would probably assume too high a learning rate for this data that has now already trained a fair way. So normally, if you wanted to train further after a batch of training like this, you would run code like this, where you find the new learning rate to now fit on in your fine-tuning to begin with. But we'll look more on that on a later lesson, but that's how you would do that for starters. But if someone was keen to I want to see the really sophisticated process for how a world-class model might be trained in terms of like long-term regime. And one place you could see that would be on Kaggle, for example. You could see quite functional, powerful notebooks using fast AI code where many cycles of training would be there, where they're doing all sorts of tricks along the way. So you do have access to much more advanced training code if you want to have a look for that. But in the end, just again referencing how helpful a graphic can be in spotting whether something's working or not versus numbers, which requires slightly more cognitive load. The confusion matrix that you want is this one where, you've got this diagonal there. And so I can almost immediately tell that it's, obviously seems to have fully worked out that particular little data there. All right. I think that'll do us for today. Hopefully that's all some help there, guys, in getting going with these classes. We've somewhat unpackaged the data block a bit, but really we're just getting started. We'll be using that more and more. So we'll be seeing that more again, but hopefully that's gotten us started on that. And thank you, guys.
Does anyone have questions for Sam?
Any more questions for me?
Just going to ask, what happens? A lot of the assumptions we've made so far are the categories are almost evenly distributed. I imagine in reality that's not always the case. What's some techniques, or does fast AI have any utilities that can assist us to maybe prop up some categories which have lower numbers?
So an example might be, say, medical data, but you mainly have 20 of a certain subcategory, and how are they going to get treated in the data set? So obviously, if you have so little data, things can get too grim to really want to deal with that. You might say that the model is going to be too uncertain for that smaller group. You can try some things like, obviously there's the augmentation to try to get more data, but you can try to create artificial data. It might be one example, or just simply oversample an underrepresented category might be another approach. There's certain advanced techniques, like there's a technique called mix-up, for example, where you take two existing data points, and you kind of find the one that's a mash of them in the middle and make that a new piece of artificial data. And there are now artificial data libraries. Maybe we'll have the chance to look at some in the weeks ahead that can kind of try to do this automatically for you, where they notice, oh, women are underrepresented. I will create some artificial examples based on what I can see here, that in the final data we give to the model, they will have equal representation. And what they noticed from this, at least in the paper, was that the model is stronger. So if you adapt for the bias to some degree, you get a stronger result. Any other questions?
So Michael briefly mentioned situations where in a classification setting you have labels that are present in one of the sets, but then are not in one of the other validational test sets.
Mm-hmm.
So I've encountered this issue in my work before, and now that I'm here, I'm curious whether you have any views on sample stratification as an approach to this.
Mm-hmm.
I found it hard to avoid with some data sets where the target label cardinality was quite high.
Yeah.
But it also concerns me, and I've seen some kind of worse outcomes in production than the validation test process would have suggested, and I'm concerned this is because the sample stratification biased the model in favor of stratified production data and made it more fragile.
Yeah.
So, just wondering if anyone here has any views on that.
All right, so to just try to summarize and repackage that, because they...
Sam, do you want to just repeat the question?
Yes, I will. All right, so partly this question is to do with maybe your number of categories is so high for something, you might see very little of a particular example in your training data, but then maybe it's overrepresented in your validation data. And how do you stop everything from just spiraling out of control there, where you've got the unusual case now the model is encountering? Is that sort of in the direction
So you got a few hundred different labels.
Yeah.
And you know the different,
They might be products, for example, a few hundred different products.
Yeah, or you know, sort of types of rocks in a big
That's
drilling
fine.
project or
Yep.
whatever
So
you
we've
like.
got rare products.
Yeah, exactly. And there's like a sort of 5 or 6 orders of magnitude in the difference in frequency between the most and the least common labels.
Yes.
So that's the kind of problem that I have in mind.
Yeah, all right. So you have rare events that may actually be really quite important. So an example might be where a pizza is not going to get delivered on time. It might be rare, but actually critical that you catch it. If you're Domino's, you know, maybe 1 in 1,000, or I don't know the numbers, but it's very important that this kind of unlikely event is caught. One way of doing that in the training is to bias the training, to adjust your loss function to find it's more important to deal with these outlier, unusual samples, that it's got to pick them up and it can't ignore them. So one answer is in the loss function of increasing the importance of getting the correct outcome for certain data. So you punish it heavier if this important data is what it's failing on. And so that can push the training to try to not just bias towards your more common data is one approach. Another question?
Sorry, just in that case, would it make sense to have two models running? One where it's just looking for that rare occurrence, and then one for the common set, and then...
That does make sense. Yeah, so if what you're simply looking for is the unusual occurrence, you might train a model for that. So an example might be at an airport where the security camera should see approximately the same thing all the time. And now if it's seeing something really quite different, maybe that's what's important now. So that's an example where you're just trying to look for a difference, and you can do that via unsupervised techniques for examples where you're just trying to do outlier detection. Might be part of it. So an outlier detection model might be quite handy sometimes.
Yeah, you
could even throw all of your rare classes into another class.
Yeah.
And then train essentially the same sort of thing. Throw them into one class and then potentially have that go for human review. I mean, it's always safer just to divert to a human, or then have a model that, you know, has learned with equal distribution of that data. I mean, it's hard when you've only got a few examples. That's where you start to look at anomaly detection and, yeah, not necessarily unsupervised, but trying to classify it out, essentially.
Okay, so that sounded like more of a strategy for dealing with sort of fat tail type situations. I was really asking more about the trade-offs of sample stratification and a train validation test split. But what you said was still useful and interesting information, so I'm actually quite satisfied if you want to stop.
All right, sure. I think based on time, we will move on, unless anyone has... I think we're good. All right, let's roll on. So thank you, Sam.
Thank you, guys.
Fantastic.
Good luck.
So from here, I just want to touch on something for a couple minutes, which is group projects, and then we will all join up into groups and let's go through the questionnaire. So before we do that, we are now in the third week of sessions, so these live sessions. And from next week on, we really want to have everyone in groups and really getting started on our group projects. So I want to give you guys a little bit more information. I don't have everything ready for you right now, but in the next day or two, it will be ready and we can start getting into groups and picking projects and stuff like that. So yeah, this week is when we're going to start organizing these project groups. We obviously have many participants in person and online. So while we are going to let people mix, because I know there's a number of people in the room who have joined the course in person but have friends who have either not got in person or maybe they've just started the course after it's kicked off and still want to be involved. So what we're going to do is we are going to let online and in-person participants work together in groups, but we would prefer, obviously we've got a whole bunch of in-person people here, if you do have a friend who wants to work with you, sort of put them down and save some space in your group. Otherwise try and keep in-person groups to in-person groups. I think it's just going to be a better experience for everyone, and it makes it easy for you guys to catch up in person and yeah, work together and stuff like that. So another important thing, this is more for our online participants, we do want people to organise based on their time zone. So I think it's probably just easiest, if you guys want to do it based on country, maybe there's, teams that want to get together based on where they're from. But I think if you can try and keep people together within sort of an 8-hour band, maybe it's Asia, Americas and Europe, we'll probably use those classifications, but just try and work in similar time zones so that you can all actually collaborate together. So there'll be that time zone. We want people to work together in time zone, and then obviously we'll probably get everyone to sort of put down what sort of domain are you guys interested in. So maybe you're really interested in computer vision or natural language processing. Maybe you want to build a recommendation system. So what we'll probably do is have a little bit of maybe a spreadsheet or a form or something like that, where you guys can just say which time zone are you in, which data domain are you interested in, and then you can sort of put yourself in the right bucket. Once you're in there might be 5 or 10 or 20 other people who are in there with you, and then you can start to go, well, I want to do this data set. Maybe 5 of you do one data set, the other 5 do the other. I think that's probably going to work best. I think it's easier if everyone just self-organizes. So that's part of our job for this week. So I want everyone to do that this week, so that next week we can confirm groups and everyone can sort of get started and start working on the problem. I'm going to put some instructions in a new channel called Group Projects, which isn't there yet, but I will create it after this. Basically just with some instructions. I have actually created an example of a few different types of data sets that you might want to use. I've actually pulled these all from Kaggle, mainly because the data's fairly available and it's a single set of instructions to actually get the data for you guys. But secondly, if you guys want to go and have a look at what other people are doing, there's heaps of code there to help you guys, do exploratory data analysis or data processing, or once you build your model, how can you squeeze a bit more performance out of it and start to go a little bit beyond the course. So all those Kaggle data sets are there for you. However, if there is another thing you want to do, you're more than welcome to. There's only a couple caveats though. First thing, if you want to use your own data set that isn't in that list or isn't just a Kaggle data set, you need to make sure that it's available for public use. Or you have written permission. I almost didn't put this in because just from a safety perspective of, data from a company getting used or whatever. But if you guys can, really focus on something that's available, it's open on the internet, it's public, that would be ideal. If someone does have a data set from their company or something like that they want to work on, just come and talk to me and we'll figure it out. You need to make sure that data set doesn't require any approvals or ethics or something like that. It's just going to be a bit too much of a headache to get everyone through that. Make sure that it's used properly, and then make sure that it's applicable to the course. We don't want huge data sets that are going to take a huge amount of time and it's just a bit too big for what we're trying to do. So make sure it's something that's fairly constrained, fairly concise, and that you think you and sort of 3 to 5 other people can get done with sort of 5 hours a week around that on average. And if you have got another data set, just I'll put just some instructions of the info that you just need to send one of the mentors or myself. Just send it through and then we'll just give you a yes or no and you can go from there. Cool. So I will put a list of example data sets. This list, in fact, I just need to move it into a different shared folder. However, at the end of the course, we're going to organize a judging panel with some prizes. Look, it's great if you can take a data set that's on Kaggle and, build a model and say, here's my metric to 5 decimal places. I did great. That's awesome. But, training the model, given the course that we're doing, is probably going to be the easy part. Obviously, it's still an achievement just to do that. But, try and think about the next step. So, you can train a model, you've got a pickle file or some weights sitting there. How could you actually use that and make something that's actually useful in the real world? So, think outside the box. Try to think about how could I send this to production. Maybe you build even just a little Streamlit app or some notebook little front end things where you can upload your image and get a prediction out. Maybe you want to, set up a little web app or something else, integrate the webcam. This is up to you guys, right? But I think you should definitely try and do this. Some ideas here is, maybe you want to go find a data set of faces and different emotions, and then you want to train a model on that. Set up your model so that it's making predictions based on an image off the webcam and saying whether you're happy or sad or you can't understand loss functions. Maybe you want to capture speech with audio, send it to a text-to-speech service, get the text and then classify it. These are sorts of things that you should be thinking about, and if it's something that you think is cool, even better, something that's going to motivate you to build it. So, we've got those Kaggle data sets there if you want to use them, but, take some time to think about, is there something else that you could do that's maybe a little bit more interesting? And when it comes to putting it on your CV or GitHub or, going to an interview with a future employer, something that is actually, more than just the Titanic data set on Kaggle, because that's going to make a big difference. Any questions on that, guys? Cool. All right, so I will create that channel and put some instructions on there if you guys want to add your own problem, and we will come up with a way to help you all get together and get into groups and get working. So now it is 7:23. We have, 37 minutes. There is a questionnaire for this week's lesson. So just like last week, we will now break off into groups. Let's go through that questionnaire. If you guys want to have a chat about data sets or group projects or whatever, either with me or mentors or each other, feel free to as well. Sound good? All right, go for it, guys. And I will pull them up on the screen for you as well. So there's our questionnaire. All right.
Yeah, exactly.
I didn't want to interrupt you because you
So I'm going to put this data set list up on the board just so you guys can get a look at it. There's obviously not a whole lot of information for you based on what's here, but maybe it sparks some ideas of maybe something that you're interested in. I know there's a couple people who are doing the course that are interested in DICOM data and chest x-rays and stuff like that. So I put a couple of data sets in there for that. But maybe just have a look at this. I'll try and make it a little bit bigger for you. And maybe what we do is we get all the computer vision people over here who are interested in doing a computer vision problem. Anyone interested in doing natural language can come to the center, and everyone interested in doing everything else can go down there. Because most people are interested in NLP and computer vision. But also one thing to note as well, if you're not sure yet, and maybe you want to do NLP, maybe you want to do computer vision, like I think what we'll do in this list online is actually, you can put your name down twice for different projects or different areas if you want. So need to figure out how this is going to work. We'll have a chat tonight, the mentors. But for now, figure out what's the thing that you'd probably most want to do, and maybe based on this list as well. And let's organize into those groups, and maybe we can actually flesh out some groups right here. So go forth.
What kind of team size would you recommend?
I think ideal is probably 4 to 6. There might be some lone wolves, or maybe 2 or 3 people who want to work together. Like the key thing is just making sure there's enough people contributing, and that you're learning from each other as well, and creating lifelong friendships. So main thing is just you guys really want to finish this project. Like you don't want to get to the end and not have it finished and not have it in something where you've ticked the boxes and it's all done. So just try and make sure that everyone in the group get a bit of a feel for how much time you all have, because not everyone has a huge amount of time. Just make sure that there's enough between all of you that you're going to keep making progress every week, and there's not going to be big gaps where no one really touches it. Sound good? Cool. All right. Rejects down there, NLP, revision. And for those online, maybe we do it. Anyone's still watching? Everyone in person is just spreading into their groups. We do have an NLP chat, computer vision chat, Tabular, and I think there's a Rexis as well. So maybe go down into some of those channels, have a chat, and maybe you guys can actually form into groups. I will leave these suggestions up here, so feel free to chat about what you guys might be interested in. And then in the next 24 hours, you can put your names down for whichever ones you're into.